Well, good morning, everybody. 11:30 on a Thursday, time for a webinar. Hey, we have a number of attendees still working their way into the webinar. So I'm going to just wait another minute or two, and we'll get rolling here. Okay, so let's go ahead and get started here. My name is Tony Andrews. I'm with Themis. I come from a development background. I've been a developer for many years. Been on application DBA a couple times, but I like the development side. I do a lot of performance and tuning consulting work, do a lot of training in those areas of performance and tuning and SQL programming, advanced SQL programming. And this particular webinar here, we're going to just touch on some of the more common topics from the application developer side that can cause some poor performance. And these topics are really good because a lot of developers out there really don't realize that they are empowered to fix a lot of performance issues going on with their programs in Db2 SQL. So we're going to touch on some of these here in the next 45 minutes. There's my email, tandrews@themisinc.com. Anybody has anything afterwards or down the road and want to email me on, feel free. Okay, if you have any questions during this, there is a chat window. I'll try my best to get to some of the questions towards the end of the webinar. You can submit the questions, in the chat window there. Questions not answered due to time constraints can be answered afterwards via some email. Okay, so our objectives for today. So we're just going to touch on some of the more common areas that cause performance, either in a specific query that we're going to hit on, a program that we're going to hit on, or really an overall application. Sometimes we may work in an overall application, and just we have a lot of programs or a lot of online transactions that just aren't performing as well as we would like them to. Maybe it's one particular table. Maybe it's a set of tables in an application, or maybe it's one particular program, or maybe it's one query in a program. So we're going to break those down a little bit over the next 45 minutes. We're going to look at data statistics. It's really important to have some good statistics on the data so the DB2 optimizers can make its best choices on how to go get the data. DBAs are typically responsible for keeping the statistics up to date. They run a utility program called RunStats that actually updates a lot of the DB2 system catalog tables that lets it inside DB2 lets the optimizer code like how many rows are on a table, and for each column in a table, what's the cardinality? For example, if we have an employee table, how many different employee numbers are there across all the data? How many different last names are there across all the data? How many different departments are there that everybody is assigned to across the data? Those are called our cardinalities. And those are real important. And we're going to touch on some special statistics. And when we realize we need some special statistics based on some what we call data skew, we have to have some special statistics run by the DBA, and we have to do something in our program to code for that. We have some examples of that coming up. Data clustering. Just like regular physical files, non-relational files, the records are stored in a certain order. Well, how should our records, or are they called rows, how should they be stored in a DB2 table? We have the ability to dictate that, and the DBAs dictate that through specifying in one of their indexes which index is going to define the clustering order of the data in that table that that index is a part of. For example, our employee table again. Should the data be in employee number order? Or should the data be in department number order? Or should the data be in last name order? What decides that? And what decides that, and we're going to get into this a little bit more, is how do we query the data? How does our programs query that data? So the clustering order of data in these physical DB2 tables has a huge effect on performance. DBAs typically don't know the exact way we should cluster the data because they don't know our application like us developers do. So we're going to talk about that a little bit more. And then we're going to get a little bit into DB2 explains, not much, but a little bit. And one of the things that we obviously want to take a look at right away is what's called table scans. Very slow process in retrieving our data. So what causes a table scan? And how do I know if there's a table scan going on? And what can I do to fix the table scan? We're going to hit on some of those topics here. Okay, so just a little bit about my experience that kind of drives me down this road of some of these presentations is, as I go out and I do a lot of performance and tuning consulting work, and I've done like over the years, my experience was highlighting a number of things. And one of the things I kind of found out years ago as a developer on some big projects that we were writing a lot of programs and queries and code for, that the majority of the problems, in applications, having to do with performance issues are poorly coded programs or improperly coded SQL. And that the poor performing SQL programs are responsible for the highest percentage of response time issues. Well, that's kind of an interesting thing because that's something that we as developers are empowered to do. I don't need DBAs. I don't need system programmers. I don't need anybody other than myself to go into a program and make some changes and get things to run faster most of the time. Now, there are times where we need a DBA and some systems people to kind of help us out. It could be something outside of our program code or our SQL code. But I find in my own experience that most of the time, probably like 80–85% of the time, I could get things to run faster by doing nothing more than changing code in people's programs. So that's big. So developers, we're very empowered. We can cause a lot of the problems in our code, but we can fix a lot of problems by changing some code. And that's what we're going to hit on here during this webinar. I find that most developers need educated in how to read and analyze the DB2 explain output. My own personal feelings on this is every developer in SQL programming, whether they're on DB2 or Oracle or SQL Server or whatever relational database system they're on, they should know how to run and analyze a DB2 explain. If a query is not performing well, the first thing we typically would like to know is what's going on in the running of that query. What's going on behind the scenes? Is it using an index? Is it doing a table scan? Is it doing any sorts involved? What's going on in what they call the access path that the optimizer has chosen to gather the data. And the only way we really know what's going on is with the explain. So if you're not educated in how to read and analyze a DB2 explain, or you're not even quite sure how to go run an explain, I would get somebody at your site to show you and set you up and start getting educated in that area. Obviously, we at Themis, we have a lot of classes having to do with the DB2 explain, classes, on performance and tuning on the Oracle side and on the DB2 side and SQL Server side. And a lot of what I talk about here today has to do across all the relational database systems. But we're going to get kind of specific into DB2 here today. There's a lot of explain tools on the market. A lot of shops have 2 or 3 different tools that developers can use to to do explains on a query or on a whole program. Okay. And I find in my experience that most developers don't understand the performance issues involved with SQL programming. Like they have a program that maybe doesn't run very well. Where do I start? Where do I go? Where do I look at? I have no idea even like what to do, to get started here. The SQL programming language allows us a lot of flexibility in how we code. There's sometimes 4, 5, 6 different ways we can write SQL statements to get the same results back. Okay. A lot of what the SQL language provides us is not very efficient with these relational database systems. Okay. We're going to hit on some of that today. So, largest performance gains, hit the application code, and we're going to talk about some of that today. Then the next steps that we go through is we look at indexes on tables involved. We tweak, maybe we add another index, and we look at statistics and make sure our statistics are up to date. Sometimes in our test environments, our statistics are not up to date. In the production environments, DBAs are usually very good at keeping statistics up to date. But in test environments, not so much, because developers are always very active, and sometimes there's a lot of different test environments. So we as developers need to kind of stay on top of that. And if we need to get some run stats run on a table because the statistics on that table are very old, then we need to communicate with a DBA. And then obviously training, coding standards, program walkthroughs, I'm huge on. Every shop should have coding standards, and every shop should have program walkthroughs. Application managers should make sure there's program walkthroughs, because that's where we learn. There's a lot of really strong people at every shop out there, and they have really good programming practices, and they know a lot of things that we're going to talk about here today. And if they don't know a lot of things, then you need to find somebody that does and have a walkthrough and have them look at your code and see if there's anything you can do to change it. And that's how we learn. That's how I learned back on some big projects years ago. We had walkthroughs on some huge projects I was involved in. I couldn't wait to go to a walkthrough because I knew going into that walkthrough with 3 or 4 people sitting there looking at my code and looking at that explain output and looking at run times and looking at the counts and all this kind of stuff, they were going to make some recommendations. I was going to learn from it. Okay, developers have 2 things in mind. My own personal opinion, in that we need to get the correct data back. Number 1, out of our query, out of our programs, reports, file outputs, whatever we're doing, the data has got to be right. The second part of what we do as developers, we need to get the results back as quickly as possible. I tend to find that getting the results back as quickly as possible is sort of put on the back burner. That as soon as developers get the correct results, they get a sign off and they start the promotion up into production. And maybe it's not running as good as it could. Sometimes there's a lot of things out there running 3 and 4 minutes that could be running in 30 seconds. Okay. So we need to make sure that we keep these 2 things in mind, that we don't just get the data correct and then we pass off performance to a DBA group. I think that's a developer responsibility. I think all developers should know how to check for performance and do explains and get their program tuned as well as possible before they pass it on to get ready to promote into production. And my own personal opinion, there's always time for a 10-minute walkthrough. Okay, so what do we look for what do we look into? We got a program, a query, or just an overall application, that's not performing very well. Well, the first thing we do, we go to the programs, and we go to the SQL statements within the programs, and we start analyzing each of the SQL statements, one at a time. And I tell developers that, if you don't know how to run explains, or you're not familiar with analyzing the output of an explain to look for some things that might be causing some poor performance, then if you can think of any way to rewrite your SQL statement in a different way to get the same results, then just try it. Just code up a different way and go run your program again. Okay. Sometimes if you can just think of a way to change one of the predicates, a predicate being one of your statements in your where logic of your query. where last name equals Andrews, that's a predicate, and first name equals Tony, that's another predicate, and department number is in, that's another predicate, so on. If you can think of how you can rewrite even one predicate a different way, sometimes it can change the way that the optimizer goes and physically gathers up the data for our result set. So we want to try to change SQL program code if it's not performing well. We also then want to do explains that we're going to get into to see really what's happening behind the scenes. We want to look at the statistics on a table. What are the statistics and are they up to date? They have a big performance impact. And is there anything in my where logic that's on a column that has maybe what we call uneven distribution of data? For example, we have in the employee table, there's employee number, employee names, other information, the department they work in. There's also the salary that they have, a bonus, and a commission that they have. Well, the column commission has a lot of different values, but 90-some% of the values is 0. That's what we call an outlier. So if I have in my where logic where commission equals some value, we need to get some special statistics on that column commission, not just the fact that it has, say, 35 values across all the data, not something more than a cardinality statistic. We need to let Db2 know that the value 0 is a large 90-some% of the data. And then when we get a DBA to run some special statistics on these type of outliers in data, then we have to do some changes in our code. And we have some examples of that coming up. Physical design, the clustering of data in the table, and what are the indexes on a table? I find that most developers don't really understand how indexes work. I mean, obviously, we know that indexes help the retrieval of data faster for our result set when we can use them. But when we see that there's an index being used, it goes deeper, and we get into this in a number of our training classes. How is that index being used? And is it used to its full capability, or is it only partially being used? And that could be a problem with some of our response time. And then there's things at the system level that we're not going to touch on today, having to do with like memory and buffer pools. And there's a lot of system parameters called zparms in Db2 that can have some effect on overall system performance. We're not going to touch on any of those, but the first one we are empowered to make some changes. The second one, we're empowered to notice some things that need to be changed and get with the DBA. And the third one, we're empowered to notice something there on the physical design, the clustering. Maybe another index is needed, maybe the clustering order of the data is needed, and can initiate a conversation with the DBA. So, next page. What causes CPU in Db2? Okay, when you run programs that have queries in them, there's CPU that has to be pulled and gathered from the operating system, and I/O. They got to go down to the actual physical files where the data resides and bring the data in. So what causes CPU? Well, the retrieval of the data from the physical file up into memory. They're called buffer pools. Okay. That has some CPU involved. And there's reports that come out from the DBA side that when we run queries, what's the get page count? In Db2, rows of data are stored on a page. And even though I may only want one row based on my where logic, the whole page of rows comes up into memory. And it's called a get page. So those things are tracked. They have some CPU involved. Data manager. We break up our data into columns and the rows based on the filtering data. Our predicates is in our where logic. The predicates actually determine out of this table what exactly do I want. Okay. The predicates actually get broke up on Db2 on the ZOS side into stage 1 predicates and stage 2 predicates. Okay. Stage 2 predicates are more expensive. Stage 2 predicates are predicates we want to try to stay away from if we can in our SQL development. There's a lot less stage 2 predicates today than there were years ago, but there still are some stage 2 predicates today that we can rewrite a different way to make them stage 1 predicates. And those are some important things to know for developers. But most importantly, out of a query, how do I know if each of my predicates, which ones are stage 1 and which ones are stage 2? And do I even have any stage 2 predicates in there? And you don't unless you do a Db2 explain. The Db2 explain will show you that, hey, you have some stage 2 predicates or you do not have some stage 2 predicates. And if you have some stage 2 predicates, we look at them and we analyze them and we see if we can rewrite them a different way. And there are some stage 2 predicates that we can write a different way that become stage 1 predicates. So we're gaining some performance right there, which kind of goes back to my first bullet for developers is like if you can think of any way to rewrite parts of your query, do it and try it and test it. You'll be surprised. Other things that cause CPU, built-in functions. We say select the integer of some salary decimal column. Select some column divided by 12. Select some kind of mathematics. Select the year of hire date. All those kind of built-in functions of mathematics, they have a little bit of overhead. So use those if you need them. Don't use them if you don't need them. Okay. Case statements, very expensive. Case statements are great to have. If then else logic up in our select. We can put case logic in other places within our SQL query, not just in the select portion. Although we see it most often in the select portion. Do I need it up there? And sometimes we do. And if I'm not bringing much data back, hundreds or thousands of rows back, and if I have it in there and I don't have it in there, you're not going to see much of a difference at all. But I've been involved in some batch programs that go through millions of rows of data. And taking the case logic out of those and putting it in the program code has saved some runtime. Okay? So we say use them, take advantage of the case logic in SQL programming. But if you're bringing back hundreds of thousands and millions and tens of millions of rows in some batch process, it may be something that you want to move inside your program code. And really, we just need to know everything that's going on in the running of a program. Summarization of columns. Am I bringing in a bunch of data and summarizing them within my code? Am I using the sum and the average and those kind of SQL functions, which are perfectly fine. We just have to realize that we're going to get behind the scenes. There's a lot of data gathered to bring us a summarization of data, in our result set. Are there any sorts going on? This is another thing in the Db2 explain that I tell developers, like, look, we're going to look for a few basic things. One of the things I want you to look for is there any sorts going on? You'll be surprised how many queries are running in production environments out there where sorts are going on unbeknownst to any developer that wrote the code and tested it in their test environments. Sorts can be caused by a lot of things. It can be caused by an order by statement, a group by statement, a distinct statement, a union versus union all. And there's some other places in SQL programming where sorts can take place. How do I know for sure if a sort is actually taking place? Well, you don't unless you do a Db2 explain. Or if you're in one of the other relational database systems, doing an explain like over on the Oracle platform. Okay? An order by statement does not always cause a sort. A group by statement does not always cause a sort. A distinct does not always cause a sort, for example. But oftentimes they do. I get into queries a lot where developers have distincts and they don't need the distincts. There are no duplicates that are going to be coming out, or group bys, or they have order bys in there and the data doesn't even need to be ordered and it's causing sorts behind the scenes that are not needed. Are there any user-defined functions, going on in the running of any of my queries? Are there any stored procedures being called out of my program? Call a stored procedure. Stored procedure is going to be running some SQL most likely. Are there any triggers involved on tables when I do insert, updates, or deletes on a table? Is that triggering another action, insert, update, or delete to another table? What kind of locking of data is going on? Locking has some overhead. So these are some of the things that when I sit down in reviews with developers and we talk about their program code, these are questions that come up. So for developers, we got to know what the programs are doing, everything that program is doing. If it's calling a stored procedure, what's going on in the stored procedure? How many queries does it execute every time I call it? How many times is it being called? you need to know how much data is typically processed. As we look at code, we talk to developers, I'll typically ask, well, how big is that table? How many rows are in that table? What's your typical result set that comes out of this when this program or this query runs like every day or every week? And oftentimes the answer comes back is, I don't know. Well, we should know. We should know. We're developers. We're in the code. We're in the data. We should know. So one of the things that I push on developers is to have counts come out, especially for batch jobs, because batch jobs process a lot more data than our online transactions do. So in our batch jobs, I force, through some standards, I want to see everything that program did, every select it did, every insert, update, delete, every open cursor, every fetch. And I want counts that come out. I want to know like what all went on inside that program. And have that displayed out somewhere or put into a report somewhere or outputted somewhere. So when a batch job runs and there's an issue, we can go real quickly to something and look at some counts. Okay, I/O. That's the actual retrieval of data out of the Db2 tables or Oracle tables or whatever that are sitting on a file somewhere, and they're brought into memory. Okay, that's what we call input/output. So how can we reduce some of this I/O and these get pages from the physical file into memory to start processing? Indexes have a huge effect. We're not going to get into index processing, in this short little presentation, but getting to know how indexes work is very important, I think, for developers that are writing SQL code. Indexes, we build indexes for a number of reasons. One of the big reasons is for faster retrieval of the data that we're going after based on our where logic. Clustering of data in the table, we have some things coming up on that. Appropriate partitioning of data. We have huge, multi-million, tens, hundreds, millions, billion row tables. We tend to partition them into pieces or parts, which actually behind the scenes is different physical files that can speed up our processing from the application side. From the DBA side, they do compression. They want to get more rows per page. And why is that important? Because as I bring a row out of Db2, the whole page is brought into memory. The more rows on that page, the more rows I have in memory. That page is going to stay in memory until these memory areas get filled up, and then pages will start dropping out. Well, if I can have as much data as possible staying in memory, Db2 knows and keeps track of what data for a table is in memory and what data for a table is down on the physical file. So if you write a query in the morning and you come in and you write a query and you execute it and it takes 3 or 4 or 5 seconds to come back, in your query tool with the result set, all that data has been retrieved and is now in memory. If you go write that query again and execute it, what do you think is going to happen? That query is going to come back in a microsecond because the data is sitting in memory now. So having the data in memory and trying to keep as much data in memory is a big part of performance and tuning also. That's what we call our buffer pool tuning. Stage 1 versus stage 2 predicates, very important on the Db2 LUW side. They don't really have stage 1 and stage 2s, but what they do have is what's called residual predicates. And the residual predicates are like stage 2 predicates, on the ZOS side. So the optimizer, we write a query, select, from, where, group by, order by. The first thing the optimizer code does is looks at the object definitions. What tables am I going after in the from clause? And when a DBA creates tables and they create indexes, that information gets stored in the system catalog tables. In Db2, they're stored in the sysibm.sys tables, sysibm.sys columns, sysibm.sys indexes, sysibm.sys, whatever. There's many of these catalog tables. When DBAs create things, that information gets stored in there. So all the object definitions are there, all the column definitions are there, all the index definitions are there. And then when the DBAs run some statistic jobs, those catalog tables get updated with numbers, all the cardinalities that we talked a little bit about. The SQL, how is the SQL written? There's a lot of times the way we write our where logic in our SQL can either give the optimizer a choice to use an index or it can take away the choice of an index. For example, mathematics and functions on columns in your where logic can have a huge effect on the optimizer not being able to take advantage of an index. If I say where hire date minus 7 days is greater than some value, if I have an index on hire date, the optimizer is not going to use that index because I have mathematics on that column in my where logic. But if I say where hire date is greater than whatever that value is plus 7 days, my logic is the same. And now it may make use of that index. So how we code our SQL is of great importance on the performance. This goes back to like one of my first couple of screens. Improperly coded SQL. That's why we have SQL standards and guidelines, and developers need to follow those, because if they don't, it can cause massive, huge performance issues. Okay? And that's just a couple of examples, the functions and the columns. There's a lot more examples in SQL programming that the way you write your SQL statements can be very inefficient in these relational database systems. And there's a couple of other areas here that we don't really get into much in at all in this. We can override the optimizer and say, hey, this is the index I want you to use, and this is the join type and all those specifics by some hints. In the Oracle world, the hints are, we can put hints in the actual SQL statement. We cannot do that in DB2. Okay, a little bit about stage 1 and stage 2. This is a little bit of information here. I'm gonna kind of roll past this one to get to some of our other screens. Some further information. Stage 1, looks at certain types of predicates. Stage 2 looks at other certain types of predicates. This kind of sums it up here a little bit more. Some of our more complex predicates. I see a lot of developers, they write some pretty complex where logic that can really be rewritten in a more straightforward, simple fashion that can have an effect on performance and minimize some of these stage 2 predicates that are going on in there. Luckily, as of version 11 on the ZOS side, there's far less stage 2 predicates than there were in previous versions. One of the tools, we actually have a class on this, one of our performance and tuning classes, and it is the use of the IBM Data Studio tool. This is an outstanding tool, nice GUI tool on the Eclipse platform to do explains and get some visual explain output. It gives us more in-depth explain information than any of the other explain tools that are out there. That's the reason why I particularly like it. And I just like the GUI, point and click and expand and all that, through the tool. But one of the things that's nice, in the screen here, as you click on any of these nodes on the left-hand side, you get information on that node. This one happens that the fetch box happens to be clicked on, and in this particular query where we don't actually see the SQL, the whole SQL statement, you can see it's got a folder up there that says stage 2 predicates. Stage 2 predicate says where that date is between some birth date and some other date. So it's a value between one column and another column. Stage 2 predicate. Where this value is between one column and another column. That could be rewritten. If that value has to be between birth date and, let's say, the other column was end date. If it's got to be between there, then birth date's got to be less than or equal to it, and end date's got to be greater than or equal to it. So we rewrite that predicate that way. And lo and behold, it goes from a stage 2 to a stage 1, and we pick up some performance. And if something is a stage 2 predicate, the index on any columns involved are not going to be chosen by the optimizer. So by moving something from a stage 2 to a stage 1 automatically opens up the use of maybe some other indexes that could be chosen. We want indexes to be used. Out of my experience in writing programs and queries, over the years on many big projects, 99% of my queries that I have running in production all over the place are using indexes. Very few times do I not want to use an index. So developers want to make sure that their queries are using indexes. What makes an inefficient SQL query? Well, statements that have poorly coded predicates. Stage 2, non-indexable. LUW has residual predicates. The way we code our where statements has a big effect on our performance. A lot of times we write queries that where the query is doing a lot more work than's needed. There's sorts in there that are needed. There's a distinct group by, order by that's not needed. Developers are coded union versus union all. Union always causes a sort, union all does not. When I go into some applications for performance and tuning, I find all the queries that have distinct. I find all the queries that have group by. I have all the queries that have order by, all the queries that have union in them. They go in some different piles, and we're going to go back and we evaluate it. I can guarantee you there's a pretty good percentage of each of those piles where that code can be taken out. Sometimes there's extra tables in queries that are not even needed. You know, we all cut and paste from other SQL statements. And do I have the tables that I need? Do I have any extra tables that are in there that for some reason did not affect my logic, but having another table in there is causing more I/O? And oftentimes I see some queries sometimes that have been running in production for like a long time that may have a 4, 5, 6 table join in them. And there's a table in there that did not get joined to. So it's what we call an orphan table. So it causes what's called a Cartesian join, and we get a lot of duplicates. And what's the first thing developers are going to do to get rid of those duplicates? They go and they stick the distinct word in their select. So they're getting rid of duplicates, but they didn't really understand why they were getting the duplicates. So when I look at people's code and I see that there's a sort going on, or if I see that they have a distinct in there, I'm going to ask them, why are you doing the distinct? Where are the duplicates coming from? So again, we're kind of going down this road of, for me to go into applications at companies and to get things to run faster, I haven't left the code yet, you know, and I'm just making changes at the code that developers should be doing, you know, in my mind. Then we start doing explains, and I want to see if it's using an index, that each query in a program is using an index, or it's doing a scan. Or how is it using the index? And we get involved in this in some of our classes that we do, our training classes. You know, is it doing an index scan? Is it doing too much screening? Is it matching on columns on the index? How is it actually probing through that index file? How is that file laid out? And what do you mean by probing? And how does that physically work? We want to make sure we are using an index, but we want to make sure we're using an index efficiently. If it has been chosen to be used by the optimizer code. Do I have any extra columns in my select? You know, sometimes one extra column in a select can cause performance issues. So are we selecting other columns that I don't even use in my program code? Am I bringing extra rows back where I have if logic in my code and I'm getting rid of it? These are all like inefficient type queries that we as performance and tuning people pay attention to and look at. This is the kind of stuff that we hit on in walkthroughs. What makes an inefficient program? Okay, you have a program being written in some kind of application code, and it's doing SQL statements. Besides poorly written SQL statements within the program code, the number one reason why programs run longer than they should is there's too much what we call conversation between their application code and Db2. Every time out of your application code you execute an SQL statement, that SQL statement actually has to leave your program and go over into the Db2 world, called an address space, and execute over there. Okay? So for you COBOL programmers, you know, if you got COBOL code, it leaves your COBOL address space and the query goes and runs in the Db2 address space. The more we go back and forth and send statements to Db2, the more expensive our program is. So just the sending of a query out of application code to Db2 has some overhead, no matter how expensive or no matter how efficient the query is. It's expensive to send that. So we need to code what I call relationally and not procedurally. Don't go get data from a query and then branch off and do 3 or 4 other select statements based on each of the rows back from our query. Get those 3 or 4 or 5 other SQL statements and build them into your main query. Make it a 3 or 4 table join. Add a couple of subqueries in there. So we're not, for every row that we're getting, executing 3 or 4 other queries and getting the next row and executing 3 or 4 other queries. That's very procedural coding. Multirow Fetch for those on the mainframe, COBOL programmers especially. Multirow Fetch. You open up a cursor, you fetch rows. Multirow Fetch has been around since version 8. It's been around for a lot of years. I tend to find many shops they don't have any programs that are even using it, and they have thousands of COBOL programs running every day in production. That should be a standard. It will, in my own experience, I've rewritten many of them, the runtime average of 35%. If you have a COBOL program runs every Saturday night, it's doing DB2 and it's running for 2 or 3 or 5 or 6 hours, I guarantee you if you go change that to a multi-row fetch program, you're gonna cut out 30% or more runtime right away. Okay, this is a little bit of like coding relationally versus procedurally. Here's a query that we tend to do fairly often in program. We get detailed data and aggregate data all on the same line. So I want the detailed data, and then I want, like in this case, the average salary based on the department that each of those work for. This is a little bit tough in programming to get both of those on the same line. So how do we do that? Well, there's a few different ways to do that. You know, in SQL, we have these what's called scalar full selects. We can put a select with a join in there up in our select. Now, what developers tend to do is they'll take that select that's up in that select, and they'll go execute that separately. So for every row that they're bringing back, they're separately going and executing an average salary. You can do it right here in your query. Much more efficient. There's another way you can do it here. You can have table expressions that'll generate the average salaries by department, and we join to that temporary table that's generated out of our table expression. And then another one, there's another way to write the query. Do a two-table join with the average salary and a group by and an order by. So here's 3 ways to get that without breaking up the code inside our program. Is one way any better than the other? No, not always. There's depends. Sometimes this join may outperform the table expression. Sometimes the table expression may outperform the join. Sometimes a scalar select up in the select portion will outperform the other two. It depends. So we have a few different ways to get something. And if you're putting an output like we saw a few screens ago, you should be trying each of these different ways. These kind of queries should be documented in application groups that says that, and with a lot of their documentation, standards, and guidelines, like, hey, if you're getting aggregation along with detail, here's a few different ways to go about it. Code all 3 of them and test them out. Statistics. We talked about statistics a little bit. We can get all kinds of statistics here. I see it's about 12:13. I'm going to roll through a couple of these. In the IBM Data Studio tool, Visual Explain tool, we can get statistics real easy. I can click on a table, and as you see over on the left-hand side there, we can get information on that table. What are the columns of the table? What are the indexes? What are some of my table space physical characteristics? How's my table partitioned if it's partitioned? And as we click and we expand all of those, we can see statistics, data statistics. How many different last names are there? How many different department numbers are there? We can see in this pink box that's highlighted here as 51,834. So as of the last time they ran RunStat, there was 51,834 rows in that table. So kind of what I like about the Visual Explain. I can do a Visual Explain, and I'm seeing a story on how the data is going to be retrieved, and I'm seeing some numbers in there that's telling me some statistics. So RunStat utility can do a lot of different things. There's a lot of special statistics that we don't get into much in this presentation. We do, however, get into them in great detail in some of our training classes. So here's an example here that I talked about. In the employee table, it has 51,834 rows. There's a column in there called commission. The commission has 31 values. That's the cardinality. That means across 51,834 rows, there's 31 different commission values. But 0 is 99% of the data. So the other 1% has the other 30 values. So for developers, once we get a DBA to run a special run stats that lets the optimizer code know that the value 0 is 99% of the data, then we need to write a couple of different queries in our program. If I'm looking for 0, we do a hard-coded 0. If I'm looking for some other value other than 0, and it's in a host variable, I specify the host variable. In this case, I have it as a question mark, and I state, and it's not 0. My commission equals some value. I don't know what the value is, but it doesn't equal 0. And that will help the best of both worlds, whether I'm looking for a 0 or whether I'm not. So when it comes to some special statistics, we have to have a DBA run special statistics. We as developers have to change our code to be able to handle it. Histogram statistics are the same way. Sometimes we may have thousands of values for a column in a table, but there might be some hotspots. So I'm going to kind of roll through here. So there's just another special kind of statistic called histogram statistics. And when they run those, they give us ranges and what percentage of data in the table has those ranges. Now when I come in and I specify a certain range like that, then the optimizer can go figure out easily, oh, I know how many rows are coming back based on that particular value. If our ranges vary a lot, or if I have to use host variables, I really can't do much other than write a dynamic SQL program so that DB2 knows at runtime what the values are and will then re-optimize at runtime. That's just a little comment on that. Clustering order of data in the table. Let me go forward here. Show you an example here. One index on the table specifies the clustering. Okay. So here's an example right here where the table, I told you before, rows are on what we call physical pages. Pages range from 4,000, up to 32,000 bytes in size. Okay, and there's reasons for like different page sizes that in some of the DBA classes that gets discussed pretty in depth. But what if I come in with a query now, and my data is in employee number order, and I come in and I say select from that table where department number equals A00. Where are my A00 rows in that table? Well, they're scattered. They're all over the place. If I have 100 people that belong to the department A00, they could be on 100 different pages. So to bring back 100 rows in my result set behind the scenes, DB2 may have to do 100 get pages. And we saw that costs CPU. If I do a lot of queries in my application where I aggregate by department number, if I do a lot of reports by department number, if most all the time when I see joins to this table is by department number and one table equals department number in this table, then this table should be physically clustered by department number and not by employee number. And that will speed things up dramatically in a lot of queries. Okay. Indexes. So just a last couple pages here. I'm not going to go through all these bullets, but why are table space scans problematic? Well, they increase CPU. There's a lot more disk I/O, and they fill up our memory. Okay. I mean, what is a table scan? If I say where last name equals Andrews, and the optimizer chose to do a table scan, it's going to read through the whole physical employee table from the page 1 to page 99999, looking for any row that has last name of Andrews in there. It's going to scan the whole file. That's slow. So why would an optimizer choose a table scan? These are some of the reasons why it may choose a table scan. And I'm not going to hit all these right now, but I wanted to present them to you. Now, we break these down in some great detail in a number of our optimization performance and tuning classes. But these are things that if a developer doesn't explain and they see a table scan, before they go talk to a DBA and say, hey, I got a query that's doing a table scan, they should go down this list of 5, 6, 7, 8, 9 things here. They will be able to figure out why the table scan has taken place, and most likely they will be able to make the correction themselves without the DBA's involvement. That's key to me. I want us developers to be more empowered. I don't want to rely on everybody else to fix my code. The problem is I find that most developers don't know where to go, where to start. So they need educated in some areas. They need educated in how to run and evaluate a DB2 explain. And they need some education like we've given here in the last 45, 50 minutes on what makes things run too long. Okay, so that kind of winds down our webinar for today. Thanks a lot for all of you that came today. Appreciate your attendance. I hope you got something out of it. I kind of mentioned off and on during the presentation, in some of our classes here, in some of our classes there. These are some classes on the application side. These are some of our more popular classes for developers, the advanced SQL, complex queries, and query tuning on the mainframe, query tuning with Data Studio. These classes are phenomenal. The stronger we get in SQL, the better we are at performance and tuning. Can most developers think of 3 or 4 or 5 different ways to write a query to get the same results? No. But if you can get strong enough to start learning how to do that, you right away become an optimization, performance, and tuning person without the help of a DBA or systems people. That's a great thing. On the Oracle side, we have some, a few classes over there. Optimization for developers, advanced PL/SQL code. There's a lot of things in the PL/SQL code that can cause some problems in performance, and how we design the programs, based on that programming language. Here's my email again, Twitter @ThemisTraining. I got pretty good at this stuff. Wrote a book a few years ago, Db2 SQL Tuning Tips for ZOS Developers. Thought I would show you that. You can find that on Amazon.com. It's got over 100 tips in there, a couple pages per tips. A lot of it, number of them, what we talked about here today. And of course, we are Themis. Education, have over 30 DB2 courses, over 400 IT courses. Everybody that teaches our classes have got a lot of experience. Those of you who might have taken them, we come on site. We also do them virtually. Some of you that attended today might have seen me or some of the others on your site, or maybe have attended a virtual class. Okay, so I didn't see any particular questions today. So if you have any afterwards, email me. If you go to our website, themisinc.com, there is a listing of some other webinars that have been done. This particular webinar will be put out there sometime in the next week or so. You can take a look at some of our other webinars if you like. And that's all I have for today. So everybody that's left here, looks like over 100 that are still left. Thanks a lot for attending. Hope you got something out of it. Hope I see you down the road, either on your site or in a virtual class. And have a great day.